Okay, so let's talk about what we did last time. So we've been talking about the fundamental theorem of calculus. And the idea about the fundamental theorem of calculus is we've done these two kinds of calculus things. Taking derivatives and taking integrals. Fundamental theorem of calculus says that there's a relationship between these two things. The first fundamental theorem of calculus we talked about last week was that if a function is continuous on the interval, and I should say this continuity is not so important. You can usually get away with not having it be continuous. But for now, let's just say it's continuous. Okay, so we have a function that's continuous, and it has an antiderivative. So antiderivative is capital F of our original function, which is lowercase f of x. And it's any antiderivative. It doesn't matter which one. You just pick one. Whichever one's most convenient for you to find. Then if I want to find the integral from a to b of f of x dx, it's very easy. I take the function capital F, the antiderivative, and I plug it in at b, and I subtract what happens when I plug it in at a. This is also, by the way, we've seen another notation for it. This is capital F of x evaluated from x equals a to x equals b. So somehow, if you know an antiderivative, you just see what's happening at the two endpoints. And knowing what happens at the two endpoints tells you something about what happens in between for this function little f of x. Now, that's one of the fundamental theorems of calculus, and there's another one. And this is, I guess we call it the second fundamental theorem of calculus in our class. And it says if I have a function which is continuous on the interval from a to b, then first off, if I take this function and I create a new function, so this function here is the integral from some constant, doesn't matter which constant it is, up to x, f of t dt. This is a function which depends on x. I plug in an x value, I get out a number. I plug in a different x value, I get out a different number. So this is a function which depends on x. So if I have a function which depends on x, I can take the derivative. So I find this function which depends on x, I take the derivative, and lo and behold, it's the function I started out with. In other words, if the f of t was what I was integrating, I integrate it, I get a new function, take the derivative, I get f of x. So another way of saying that, you could also say that the integral from c to x f of t dt is an antiderivative of little f of x. Because if we took the derivative of it, we got the original function. That's the definition for being an antiderivative. All right. So now we see that these two things are related. And that makes it really nice on us, because we may be interested in trying to figure out something like what's the integral from a to b of a function. And we'll go through some examples of why that might be interesting for us to know. And now it turns out, well, all we have to do is do something like what we did over here, where if we can figure out the antiderivative, very easy, plug in points, and we're done. Now, this is a very simple way to state the second fundamental theorem of calculus. But we can combine that theorem with the chain rule to get the following fact, where instead of integrating from some constant up to x, we can make it look much more complicated. So here I'm integrating from some function of x to some other function of x, f of t dt. And I take the derivative. And so if I just combine what I know about the fundamental theorem of calculus with what I know about the chain rule, lo and behold, it's very simple. It's f of g of x times g prime of x minus f of h of x times h prime of x. Now, this looks a lot like the chain rule. Of course, the chain rule we had f prime here. You might say, well, where don't we have an f prime here? Well, we essentially do, because we're not taking the derivative of f. We're taking the derivative of essentially the antiderivative of f. So that's why there's no prime there. All right. So here's a question from the homework. Let me make sure I get this right, otherwise I'll get myself in trouble. Okay, suppose you know the following. The integral from c to x, g of t dt, is equal to x squared plus x minus 6. And I'm going to ask two questions. Question number 1, what is g of x? Question number 2, what can we say about c? This is actually a problem that came from the homework, not one that you were assigned, I don't think. But it came from out of the book. So we want to figure out g of x. So we look at this and say, well, really we have this g function is inside the integral. So how can I get just plain old regular g of x instead of having this integral that involves g? Yeah, I can take the derivative because I have this fundamental theorem which says if I have this integral and I take the derivative of it, I just get back the function that's inside. And our function is perfectly set up for this because we're going from a constant to x. So it says if I take the derivative over here, let me use a different color here. So I take the derivative of the left-hand side. That should be the same thing as if I take the derivative of the right-hand side. Because if I take the derivative of two things which are equal, their derivatives have to be equal. Okay, and we said over here the derivative of the left-hand side was g of x. What's this derivative turn out to be? 2x plus 1. Okay. Now we're doing good. We figured out g of x. Woohoo! We have another question. What can we say about c? C is some constant. Can c be arbitrary? Yes? We can. So we could integrate for g of x here because we know what g of x is now. And we could figure c out. I think there's a slightly easier way to go about this. So let's hide the derivatives. Go back to this statement here. Look at this relationship over here. Is there any x value where we don't even have to do anything? We know what happens at a specific value of x. Is there some x value? I plug it in. I say, I know that. Oh, say, can you see? See? All right. What happens if I put in x equals c? I go from c to c, and the integral from c to c is 0. Okay. So for this one, let's try x equals c. So the integral from c to c, g of t dt, by definition, has to be equal to c squared plus c minus 6. But as we said, this is 0. So now we have 0 equals c squared plus c minus 6. Now, c squared plus c minus 6, can we do anything with that? We can factor c plus 3 times c minus 2. So what can c be? Yeah, c can be negative 3 or 2. Either one works. Those are the only two that work. So it's important here to realize that, of course, the integral from c to x, g of t dt, it is an antiderivative. But it's not any arbitrary antiderivative. It's actually a very specific one. So here, when we're saying c equals 3, 2, we're basically trying to limit down to say, if I want to get this specific antiderivative, if I want to get the antiderivative x squared plus x minus 6, I have to choose one of these two values for c. If you choose a different starting value for c, you'll get a different antiderivative, which means essentially what will happen is the constant changes. Okay. So there's an example of how you can use the second fundamental theorem of calculus to answer questions. So let's go back to just integration. So the big question, of course, is why are we doing this? What is it useful for? So the idea about integration, we said this before, but it's worth repeating. The idea is to break into small parts and add them up. And this is a terrible sentence grammatically, but that's okay. It's the intuition that we want to focus on, not my bad grammar. So we're going to take something, we're going to break it up into small pieces. And the small pieces we say, well, I understand what's going on with the small pieces. And then I'm going to add all the little pieces up, and then I say, okay, now I understand what's happening with the whole thing. So here's a very simple example. Suppose I know how something has changed. So I know a rate of change which is constant. Now let's actually put something in here. So Suppose, I don't know, I have a bucket, and I'm pouring water in. And I know that water is flowing in there at the rate of 1/10 of a gallon per minute. So I guess maybe I shouldn't say flowing water, I'm just trickling water in. It's going in very slowly. But I know it's going in at a constant rate. And I say, okay, suppose I know I have this going on. I know it's always 1/10 gallon per minute. It's not changing at all. And I ask the question, well, how many gallons are in the bucket after 5 minutes? Now, this is hopefully not a very hard question to figure out. 1/10 of a gallon per minute went in. I let it go for 5 minutes. There's one thing I didn't say. Let's suppose it starts off empty. How many gallons are in there after 5 minutes? How do you figure it out? Yeah, you take your rate times the length of time. 1/10 times 5, a half. Half a gallon. Now, in this case, we were lucky because our rate of change was constant. So we understand what goes on when rates of change are constant. But, of course, the world is not so pleasant. The world likes to have things which change. And so when things change, things get more difficult. Suppose I now have my same bucket, now purple, color coordinated. Water is still going in. But now it's not going in at a constant rate. Now the rate varies. So the rate is 1/20 plus T over 10 gallons per minute. So in other words, initially at time 0, I'm just pouring in at a rate of 1/20. Then at time 1, slightly more goes in. At time 2, even more. So it's like I'm slowly turning the spigot. So that as time goes on, I get more and more water flowing out. Okay. Same question. Suppose I start off with an empty bucket. After 5 minutes, how much water is there in the bucket? Now it's not so clear. Because I can't just say, well, take 5, which is the length of time, times what? What rate? Because the rate changes. So here's the way we think of it. So 1/20 plus T over 10 is some here rate of gallons per minute. And I'm going from 0 to 5. Well, what I can do is I can think of basically breaking it up into little tiny pieces, chopping up into little tiny pieces. And I say, well, what happens at any one specific time interval? So here, suppose I'm at T. And I look close to T. How much water goes in here at this point? Sorry, this pen is dying. All my pens are dying. Time for new pens. Well, the amount of water that's going in here is 1/20 plus T over 10. That's the rate at that time T. But I want to measure how much water went in, not the rate at which it's going in. So I need to times it by a length of time. Now, the trick here is to just say, well, I'm going to chop up into very small lengths of time. In fact, really super tiny, so small they're almost like infinitely small. We call it dt. So if you think about it, notation-wise, this is how many gallons per minute at time t. And then this is our length of time t. So in other words, this is a length of minutes. So if I take gallons per minute times some measurement of time, which is minutes, then this is a measurement of how many gallons. How many very, very small amount of gallons flowed in at time t. Now that's just one little piece. I have to do it for every single one. So what I did is I chopped it up into little pieces, and then I'm going to add everything up. Now, how do we add everything up? Well, we sum. The integration is nothing more than really adding up lots of little tiny pieces. So I'm adding up all the little tiny pieces of water that float in there. And I'm starting at time 0, and I go to time 5. And now this is easy for us to do. And unit-wise, it makes sense, because the inside of the integral is gallons, and then I'm just adding up gallons, so I get gallons out. So I do end up with something that makes sense. I get a gallons out as my answer. Using the fundamental theorem of calculus, well, the integral of 1/20th is 1/20th t, and the integral of t is t squared over 20. Sorry, there's a t over 10, becomes t squared over 20. And evaluate from 0 to 5. So that's 1/20th times 5 plus 5 squared over 20. Then you subtract what happens when you plug in that time 0, which is 0. And this is 5 plus 25 makes 30. Divided by 20 is 3/2. So in this case, after 5 minutes, 3/2 of a gallon or a gallon and a half went in there. Okay. So integration can be used to tell you what the total is if you know how something is changing. Now, in this case, the 1/20th plus 1/10th t, that was a measurement of how something is changing. It's a rate. And if we look at what the fundamental theorem of calculus says, if we look at, say, this part of the fundamental theorem of calculus, it basically says the following. If I look at the integral from a up to b of f prime of t dt, well, what's an antiderivative of f prime? F. Because f prime is the derivative of f. So an antiderivative of f prime is f. So this is f of b minus f of a. And we've done nothing more sophisticated than basically use this formula here. F prime of t tells us the rate of change of f with respect to t. So this is measuring how fast f is changing. That's the f prime of t. dt, this is a small time interval. Now, when I multiply the rate of change, how f is changing, times the small time of change, this combined on the inside is the amount of change at time t. And I should say very small infinitesimal amount of change, because dt is a very small interval, is the way to think of it, the intuition. So that the inside is basically what happened at time t, how much it changed. And then add up all the change from a to b, that's the total change. So this here, as I add up to find the total change. And look, what is f of b minus f of a? Well, f of b is what I am at t equals b. F of a is what I am at t equals a. So this is also the total change from t equals a to t equals b. Okay, so it's nothing more sophisticated than this. Another way to write this, convenient for some problems, is you can rearrange this and say that f of b is equal to f of a plus the integral from a to b f prime of t dt. How do we interpret this? Well, it says if I want to know the value of the function at b, now what the function is, it just depends on the problem. Function can be anything. But if I want to know what's happening with the function at b, I can take what I know about what's happening with the function at a, then I add to it how the function changed. So this is the function at a, plus this is how the function changed in going from a to b. So, of course, we get the function at b. This is not very hard to see if you add f of a to both sides. All right. So here's some examples. Suppose I look at a velocity problem. Now I know at time t equals 2, I am 10 feet from the wall. So I'm just moving back and forth to this wall. I also know that if I look at my position, s prime of t, if s of t is how far I am from the wall, s prime of t tells me how my distance from the wall is changing. This is equal to, let's try 1 minus, let's make it more bigger numbers here. 10 minus 20 sine t. Hopefully I end up not walking into the wall. I may have. We'll see. All right. So I know my position from the wall, t equals 2. So in other words, this says that if I look at this information, this tells me that s of 2 is 10. So at time 2, I am 10 feet away from the wall. My position at time 2 is 10. I know how my position from the wall is changing. I know the derivative. So here's the question. What is s of 10? So after 10, I guess I should say what my units are. This is feet per second. So time here will be measured in seconds. I'm moving it fast enough to make it interesting. Usually by the time I figured out the answer, I already will have moved back and forth from the wall a few dozen times. Okay. So how do we figure this out? Well, it's basically just this same equation here. I want to figure out s of 10. And one way I can do this is I can say, well, I know where I start at time 2. I start here. At time 2, I started off 10 feet away. And then I know how I'm changing. So to go from time 2 to time 10, well, that's the same as integrating from 2 to 10 how I'm moving s prime of t dt. Well, this is not too hard because I know all these values. S of 2 is 10 plus the integral from 2 to 10. I used 10 way too much on this problem. I should have used different numbers. So I plug in what I know. Now I just go through and work it out. So I have this 10 here. What's the integral of 10 minus 20 sine t? Yeah, 10t minus, what's the antiderivative of negative sine? Or, just sine. Well, we come over here. The antiderivative of sine, or the indefinite integral of sine, is negative cosine. So the antiderivative of sine is negative cosine, then it's negative 20, so it becomes a plus 20 cosine t. Then evaluate from t equals 2 to t equals 10. So this is 10 plus 100 plus 20 times cosine of 10. That's t equals 10 minus 20 plus 20 cosine of 2. And we have to stop here because we don't know what cosine 10 and cosine 2 are. But you get the basic idea. Now, there is a little bit of difference here. Let me come look at velocity for a second. So we've talked about velocity before. Velocity function, the v of t, is the derivative of position. So if we think of s of t as our position function, v of t is velocity. So what's the difference between, say, the integral from a to b of v of t dt versus the integral from a to b of the absolute value of v of t dt. Is there a difference? Are they the same thing? Well, sometimes they are the same thing, which helps to throw in some confusion. Now, this one is very simple because we're exactly in the same position we were over here. So this is simply s of b minus s of a. So the position I'm at time t equals b, subtract the position I'm at time t equals a. So this is basically how far off I am from where I started, our distance between start and end. But what about this one? Well, let's go through a specific example, and then we can talk about what they represent. Suppose we'll do something that we've probably seen before. Let's suppose v of t, again, let's do sine. Actually, let's do cosine. Cosine will be easier. Suppose I say v of t is cosine of t. And let's look at the integral from 0 up to pi cosine of t dt. Well, we know the antiderivative of cosine is over there on the board. This is sine of t from t equals 0 to t equals pi. Sine of pi minus sine of 0. What's sine of pi? 0. Sine of 0? 0. So this is 0 minus 0, or in other words, it's 0. So what does that tell us? Well, it tells us if our velocity is cosine, and we go from time 0 to time pi, and we got 0 out, what does that tell us about where we started related to where we ended up? We ended up in the same place. Now, if you look at what the graph of cosine looks like from 0 to pi, it looks like this. So initially, on this part of the graph, between 0 and pi halves, where v of t is positive, so in essence, we're increasing our distance from where we start. But from pi halves to pi, what's happening? We're decreasing our distance. Or in other words, you could say that this is a positive, we're moving in a positive direction. This is negative, we're moving in a negative direction. So pictorially, if this is our starting point here, first thing we do is we go this way from t equals 0 to t equals pi halves. And then at t equals pi halves, we go this way. So that we end up back where we started. Now, what about the integral from 0 to pi of the absolute value of cosine of t dt? What will happen with that? Well, in the absolute value of cosine of t, it would look something like this, where essentially I take wherever negative and I flip it up, so that's positive. So if I look at this function here, well, just looking at the graph, there's symmetry around pi halves. So this is twice, if I went from 0 to pi halves, cosine of t dt. If you don't like that, you can just say, well, integrate from 0 to pi halves, cosine t, and integrate from pi halves to pi, negative cosine of t. That's the same as taking the absolute value of cosine t from 0 to pi. So this is 2. And then same antiderivative as before, sine of t, evaluate from t equals 0 to t equals pi halves. So this is 2 times sine of pi halves minus 2 times sine of 0. And of course, sine of 0, as we said before, is 0. What's the sine of pi halves? It's 1. And so in this case, we got out 2. So that here, when I took the derivative of velocity, I got a different answer than when I took the derivative of the absolute value of velocity. Now, velocity measured how far we moved. the total amount of change in our position, which was in our case was 0. Where did the absolute value measure? Well, the absolute value measures here. It comes in. Let me use a different color. It doesn't distinguish between walking left and right versus walking left versus walking right. It just says, well, how far did you walk? Now here it says when I walked from 0 up to pi halves, really this distance is length 1. So from 0 to pi halves, I walked length 1. And then how far back did I walk? Well, I walked length 1 again. So instead of being the distance between where you start and end, if I do look at the integral of the absolute value, this is going to be the total distance traveled. Now, oftentimes, they're the same thing. In particular, if your velocity is always positive, it doesn't matter which one you look at because the absolute value is meaningless. This only comes into play whenever you have an absolute value that can change signs.